In Lesson 1, we argued that physics begins not from objects or geometry, but from distinguishability. But this immediately creates a deeper question. If distinguishability requires at least two things, then what exactly are those things? If we call them objects, physics has already entered. If we call them particles, physical structure already exists. If we call them points, geometry already exists. But our goal is to begin before all of these assumptions. So at the most minimal level, we avoid all physical interpretation. We simply say, there exist possible states. Nothing more is assumed. We give a name to the collection of all possible states. We call this collection S. S is called the state space. But the word space here does not mean geometry. There are no coordinates. There is no physical distance. There is no predefined structure. S is simply the collection of all possible variants. Mathematically, we write S equals the set of S sub I. This compact expression contains the foundation of the framework. The symbol S is a capital letter representing a set. A set is simply a collection containing elements. The equal sign defines what S means. We are specifying the content of the collection. The curly braces represent a set. Everything inside the braces belongs to the collection. The symbol S represents a state. The index I is only a label. It does not yet represent geometry, coordinates, or physical ordering. It is simply a way to distinguish different possible states. The expression means S is the collection of all possible states. Nothing more is assumed. At this stage, we intentionally do not define what a state physically is. This is not a missing detail. It is a deliberate foundational decision. If we define a state as a point, geometry has already entered. If we define it as a particle, physics has already entered. If we define it as energy, physical quantities already exist. The framework intentionally avoids all of these assumptions. So the only thing we say is this: S sub I is a distinguishable possible state. No additional structure is assumed. At this level, there are no coordinates, no distance, no time, no neighborhood, no geometry, no measure. S is a structureless collection. We begin without structure because the goal is to derive structure later. If structure is inserted at the beginning, then it is no longer a result. It becomes an assumption. Now we return to the difference operator introduced in Lesson 1. But now we understand more deeply what S represents. S cross S means selecting two states from the collection. This creates an ordered pair. An ordered pair contains a first state and a second state. Examples include S1, S2, S3, S7, and S5, S5. The cross symbol represents the Cartesian product. This means the collection of all possible ordered pairs. Now the meaning becomes clearer. The operator D assigns a non-negative value to every pair of possible states. In simpler language, D of S sub I and S sub j equals the amount of distinguishability between them. At this stage, D is still not physical distance, it is not geometry, it is only the strength of distinguishability. Now we reach the relational principle. A state is defined only through its differences from other states. The expression means a state is identified through the entire collection of its distinguishability relations. Its identity is relational. This leads to a powerful consequence. There is no absolute state. There are only relational states. All information exists comparatively. This decision reaches deeply into physics. It connects the observer problem in quantum mechanics, coordinate dependence in relativity, and reference problems in information theory through a single relational foundation. At this stage, we have established four essential ideas. S represents all possible states. S sub I represents a particular possible state. No predefined structure exists, and all structure will eventually emerge through distinguishability. We do not begin from objects. We begin from the collection of possible states that exists before geometry, before coordinates, before physics, and before structure itself. In the next lesson, we will study the deeper properties of the difference operator. We will explain why D is not a metric, why this decision changes the foundations of physics, and why reality disappears when distinguishability vanishes.